Hello friends, welcome you all to the 9th lecture on function analysis and its application. In this lecture, we will discuss the linear space CAB as normed linear space but not a Banach space. The contents as follows. The Banach space CAB, actually linear space CAB is a normed linear space under the norm this and a Banach space, but norm defined as follows: norm 2, then it is not a Banach space. The Banach space CAB in the linear space, this is in the linear space CAB of real valued continuous functions on closed interval AB, define two norms as follows: norm F1 equal to max when max value of mod Fx when x lies between closed interval A and B, and if norm defined as integral a to b mod fx dx and f is the element of CAB. CAB, the real valued continuous function under the closed interval AB. Then these norms that first makes the linear space into a Banach space, but the second does not. Second follows the all condition of non-linear space but not Banach space. Explanation: since a real valued continuous function on closed interval is bounded, CAB can be proved a Banach space under the norm F1, exactly in the same manner as example 3rd discussed in previous lecture. Okay. Already we have discussed the example of Banach space with this norm. Okay, so it can be avoided here. We now show that F2 defined as this is actually a norm on CAB and CAB is not complete. Let us prove it. Vector addition and scalar multiplication are defined by, suppose f and g belonging to CAB as vector, then f plus gx is fx plus gx, and if alpha be scalar and f belonging to CAB, then alpha fx, that is alpha fx. Let us prove the all condition of non-linear space. Since mod fx greater or equal to 0, and we know that modulus value of any point non-negative, so mod fx greater or equal to 0 for all x belonging to AB. This implies that integral mod fx dx, here mod fx always greater or equal to 0, then integral a to b mod fx dx greater or equal to 0. First condition satisfied. Here norm f2 greater or equal to 0. Second, norm f2 is equal to 0. Norm f2 defined as this integral a to b mod fx dx, then we can write norm f2 is equal to 0. This implies that integral a to b mod fx dx is equal to 0. If and only if the integral mod fx dx is equal to 0, it means mod fx is equal to 0. This is mod value, so we can say that fx is 0. Fx is 0 means f is 0 function. Hence, norm f2 is equal to 0 if and only if f is equal to 0. Second condition satisfied. Third, let alpha be scalar. Then norm alpha f equal to integral a to b mod alpha f x dx. Alpha f can be written as alpha fx. So, mod alpha fx dx can be written as integral a to b mod alpha fx dx. So, this can be written as mod alpha mod fx. Alpha free from x, so we can write mod alpha integral a to b mod fx dx. That is, this is norm f2. Therefore, norm alpha f2 equal to mod alpha norm f2. Okay. Third condition also satisfied. Fourth, let f and g belonging to CAB, then norm f plus g equal to integral a to b mod f plus g x dx as per the statement here. Okay, so f plus gx can be written as mod fx plus gx as this. We know that mod fx plus gx less or equal to integral a to b mod fx plus mod gx dx. That is a to b mod fx dx plus integral a to b mod gx dx. That is norm f2 plus norm g2. Hence, CAB is non-linear space under this norm. Completeness of CAB. To show that CAB is not complete, consider the sequence Fn belonging to CAB defined as follows. Let C belongs to closed interval AB. Okay. Then Fnx defined as this. Fnx is 0 if x lies between a to c minus 1 upon n, and Fnx is equal to nx minus nc plus 1 when x lies between c minus 1 upon n to c, and Fnx is equal to 1 if x lies between closed interval CAB. Okay. Here Fnx is continuous in closed interval AB. Let us show that Fn is a Cauchy sequence in CAB and does not converge to an element of CAB. Okay. Let Fn be a Cauchy sequence, that is norm Fm minus Fn. We have to check norm Fm minus Fn tend to 0 as Mn tend to infinity. Let us check the Fn is a Cauchy sequence or not. Here norm fm minus fn 2 is equal to integral a to b mod fm minus fn x dx. So this can be written as, per this definition, we can write fm x minus fn x dx. Here interval AB defined in 3 steps, A to C minus 1 upon n and C minus 1 upon n to C and C to B. So this interval AB can be divided in 3 parts: integral A to C minus 1 upon n plus C minus 1 upon n to C plus C to B mod fmx minus fnx dx. Okay. So here value of fmx and fnx is 0 in interval a to c minus 1 upon n. So this integral a to c minus 1 upon n, that is 0 minus 0, that is 0. And third integral c to b fnx is 1. Okay. So fmx is 1, fnx is 1. So third integral also 0. We have integral c minus 1 upon n to c mod fmx minus fnx dx. This integral c minus 1 upon n to c mod fmx minus fnx dx. Okay. That is, this integral can be written as less or equal to c minus 1 upon n to c mod fmx plus mod fnx dx. Okay. So norm fm minus fn under the given norm 2 less or equal to integral c minus 1 upon n to c mod fmx dx plus integral c minus 1 upon n to c mod fnx dx. Now we solve this integral and this also. Now we evaluate first integral. Integral c minus 1 upon n to c mod fnx dx. Okay. Second integral equal to integral c minus 1 upon n to c. In this interval fnx is nx minus nc plus 1. Okay. So integral c minus 1 upon n to c mod nx minus nc plus 1 dx. Okay. So c minus 1 upon n to c mod nx minus nc plus 1 is nx minus nc plus 1. We can integrate it nx square upon 2 minus ncx plus x c minus 1 upon n to c. Now we solve it. Putting the value of x as c minus 1 upon n in this and this also. So after solving, we have 1 upon 2n. Okay. Here detailed calculation. So integral c minus 1 upon n to c mod fn x dx equal to 1 upon 2n. Similarly, we have integral c minus 1 upon m to c mod fm x dx is equal to 1 upon 2m. Okay, therefore, from this we have norm fm minus fn less or equal to 1 upon 2m plus 1 upon 2n. This is tend to 0 as m tend to infinity and n tend to infinity. That is norm fm minus fn tend to 0 as mn tend to infinity. Therefore, fn is a Cauchy sequence in CAB. But this sequence is not convergent. Suppose if possible, let fn converges to f in CAB as n tend to infinity. Then here norm fn minus f under 2 norm can be written as norm fn minus f 2 equal to a2 c minus 1 upon n mod fn minus f x dx. Okay, so this one a to c minus 1 mod fx dx. First is a to c minus 1 upon n mod fx. Why? Because a to c minus 1 upon n value of fn x is 0. Okay, so here first 0 minus f x, that is mod fx, and second c minus 1 upon n to c mod fn x minus fx dx plus integral c to b plus this one and plus this one. Okay, so here second integral c minus 1 upon n to c mod fn x minus fx dx, and in third integral c to b we have mod fn x minus fx, that is value of fn x in interval c to b is 1. It is given here. Okay, so we have here integral c to b mod 1 minus fx dx. Okay, hence norm fn minus f under norm 2 tend to 0 as this one tend to 0. Okay, when it is possible, here modulus value of fx, this, here also modulus value, and here also modulus value. All are positive, So it is possible to 0 when this integral 0, this is also 0 and third be 0. When it will be 0? In first integral, in this interval a to c minus 1 upon n mod fx dx is equal to 0. In this interval a to c minus 1 upon n value of fx 0 as n tend to infinity. So n tend to infinity, this integral a to c, when a to c fx is 0. Okay, so fx is equal to 0 when x belonging to closed interval a to c. And second integral, if n tend to infinity, then both limit same, c to c. Then second integral automatically 0. And third integral, this will be 0 when the value of fx is 1 in closed interval cb. Okay, so this one 0 when x belonging to closed interval cb, fx is 1. When fx is equal to 1, for x belonging to cb, then this integral 0. So norm fn minus f under the given norm 2 tend to 0, fx is 0 when x belonging to AC and fx is equal to 1 when x belonging to CB. For this possibility, fx is equal to 0 for all x belonging to AC and fx is equal to 1 for x belonging to CB, the function is discontinuous at x is equal to c. Okay, so function is discontinuous at x is equal to c. So f is not an element of CAB. Okay, why? Because CAB is a continuous real valued function. Here f is discontinuous at the point C. This contradicts that f belonging to CAB. Hence Fn is not convergent. And so CAB is not a Banachspace. In this lecture, we have discussed the linear space CAB as a nonlinear space but not a Banachspace under the norm this. Norm F2 is equal to integral a to b mod fx dx when f belonging to CAB. These are the references which have been used in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Naresi. Second, introductory function analysis with application, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, written by Waterrudin. Thank you for your attention.